Good morning to all my dear students. This is B. Anita, Assistant Professor of Physics, Department of Science and Humanities, CKCET. Now I am going to explain about strengthening methods. Okay. What is meant by strengthening? The strengthening means increasing the strength of metals. Okay. Dear students, already we have learnt about plastic deformation and dislocations in the previous topic. When an external force or shearing stress is applied on a material, there will be a movement of atoms in many interatomic distances. So, dislocations are generated. The plastic deformation or the permanent change depends on the dislocations. So, if we reduce the movement of dislocations, the strength of the metal can be increased. What are the methods used to restrict or resist the movement of dislocations are called as strengthening mechanisms. There are four methods to increase the strength of the metals: the strain hardening, refinement of the grain size, solid solution strengthening, and precipitation hardening. Now we see one by one. First one, strain hardening. What is called as strain hardening? It is also called as work hardening or cold working, because it is done on low temperature. So it is called cold working. It is the process of making a metal be very strong. This is done by plastic deformation. Okay. The plastic deformation at a temperature very low than the recrystallization temperature. What is meant by recrystallization temperature? The temperature at which new grains begin is called the recrystallization temperature. Now we see the mechanism of strain hardening. When a metal is plastically deformed, dislocations are generated. See, these are the dislocations. These dislocations are generated. Okay. This dislocation density increases by cold temperature. So, the distance between the dislocations, okay, is decreases. That is, the gap in between the dislocation decreases. So, they will start to become pinned. Okay, pinned means they are unable to move. Okay, so all the dislocations are pinned together at this place. Okay, due to pinned process, the movement of dislocations reduced. Okay, our aim is to reduce the movement of dislocations. Here, due to the pinned process, the movement of dislocations are reduced. So the strength of the material increased. Okay, so here this is one new grain. Okay, see in this picture, the first one, these are dislocations. Here the dislocations are pinned. Here this one is the new grain. Okay, new grain starts. Okay, next one, see what are the effects of grain hardening. What are the effects of strain hardening? Oh, it improves the hardness, it increases the tensile strength, it reduces the ductility and plasticity, and also it increases the yield strength. Okay. Now what are the limitations of strain hardening? The materials become more brittle. Brittle means it will break easily. It produces internal stresses in the metal. Okay. It produces a distortion in the grain structure also. and also it requires greater energy to deform a metal plastically. So these are the limitations of strain hardening. Now we see one video clip. Here how the work hardening or cold working is done. The first one, example, forging. The forging means mechanical reshaping of metal by hammering or pressing. Pressing means the compression force. Okay, the compression force is given. See the magnet, the shape of the magnet changes. Okay, due to the compression. Okay, now the next one, example, rolling. Rolling is thinning of a metal sheet by pressing in between two rollers. Here there are two rollers, on the top one, the bottom one. In between the two rollers the metal sheet is moving. Okay, so the rollers pressed the metal sheet shape changes. Okay, this is also one example for cold working. Okay, the next one we are going to see about refinement of the grain size. How the grain size affects the mechanical properties. Okay, so before going to see that, we should know about a particle. A particle consists of more number of grains. Similarly, a ferromagnetic material contains more number of domains. Here, instead of domain, we can say what is the grain. Each grain having different orientations. For example, this grain, here the orientation is in this direction, means in this grain the orientation is in this direction. Okay, in this domain the orientation is in this direction. For example, this domain, the orientation is in this direction. The blue color line shows the grain boundary. The movement of dislocation is stopped by this grain boundary. Okay, why the movement of dislocations is stopped by the grain boundary is, the reason is two grains are different orientations. It is very difficult to change the direction of orientation. So if the grain size is reduced, the movement of dislocations restricted. Okay, because each grain boundary resists the movement of dislocation. See, for example, this grain is reduced means, see, for example, this is a grain boundary. The dislocations will not move from this point to this point. Okay, because the grain size is reduced. This is the grain boundary. Okay, the dislocations will not cross over the grain boundary. Okay, so the grain size reduction also improves the strength of the material. In this picture also the same one explained. Here this is the grain boundary. This is one grain A, this is one grain B, that is different grains. Okay, now one small two more question here. Hall-Peck equation. This Hall-Peck equation gives the relation between the yield stress and grain size. Okay, the equation is sigma yp is equal to sigma 0 plus k divided by square root of d. The sigma y is the yield stress. Here sigma 0 is the friction stress. Okay, or the resistance to dislocation motion. K is the constant and d is the grain diameter. Okay, now Next one, solid solution strengthening. In this case, the metal to be strengthened is mixed with some impurity atoms. Okay. When it is added with impurity atoms, they are occupied in substitutional sites or interstitial sites. These impurity atoms restrict or reduce the movement of dislocation. Okay. How means the smaller substitutional atom creates tensile lattice strain to the host atom. These are the host atoms. These are the host atoms. This one is what is substitutional. Okay. So smaller substitutional atom creates what is a tensile lattice, but larger substitutional atom creates one compressive lattice because the size is very much greater. Okay. Now we are going to see about the factors affecting the solid solution strengthening. What are the factors affect this solid solution strengthening? It's very important. First one is difference in between solute and the solvent atoms. Then amount of solute added. The nature of distortion produced by the solute atom. These are the factors affecting the solid solution strengthening. The next one, what is the precipitation hardening or age hardening? Okay. It is a type of a heat treatment. Okay. In this type also, solid impurities or precipitates are used for the strengthening purpose. Here, the metals and alloys need to be maintained at very high temperature for long time. Okay. Since it is maintained at a high temperature for many hours, it is also called as age hardening because it takes large time. Okay. In this process, what will be taken by first high temperature is given, then it is cooling. Okay. Then medium temperature is given, then finally cooling again. So this is the process we are going to do in this precipitation hardening. There are two separate heat treatments. One is solution heat treatment and the next one is the precipitation heat treatment. In the solution heat treatment, the materials are heated until all the solute atoms are dissolved and to form a single phase solution. Okay. In the precipitation heat treatment, first it is heated at an intermediate temperature. When it is heated at intermediate temperature, one atom diffuses to form other one. Okay. So the precipitate begins to form. Now it is cooled to stop the precipitation. Then again the second phase particles, that is the formed precipitation particles. Okay. So these particles resist the movement of dislocations. So this is the process of precipitation hardening or age hardening. Okay. Now in this video, how the age hardening is done in gold metal is explained. See here.
One of the questions that we most frequently receive concerns the chance to harden alloys using age hardening, a specific thermal treatment. This question is very common because every manufacturer knows how useful it is to have a hard, strong jewel, especially with thin or filigree parts that are so commonly used today. It is the kind of alloy used that defines whether an item can be age hardened or not. Sterling silver is well known to be age hardenable, whereas, for example, a traditional brass does not increase its hardness in this way. How does age hardening work? In a nutshell, The heat which is given to an item at a certain temperature and time induces a transformation in the alloy's microstructure, which makes the alloy harder and less prone to bending or scratching. The effect is measurable with a hardness meter, and it can be qualitatively experienced when trying to deform the piece. The working temperatures commonly used for silver and gold alloys are between 300 Celsius degrees and 450 Celsius degrees for a time of approximately 90 minutes, followed by an air or furnace cooling. A regular 750 gold yellow alloy is easily hardened at 300 Celsius degrees for 90 minutes. This is the so-called single-step age hardening, which works just fine on hardenable gold alloys. Silver alloys instead will benefit from a preliminary step named homogenization. This is a high-temperature annealing made between 700 and 740 Celsius degrees for 40 minutes, followed by an immediate water quench, allowing the microstructure to obtain the best condition for precipitation of copper particles in the silver matrix, later done at lower temperature. This is the two-step age hardening process. The actual age hardening process after homogenization is done at 300 Celsius for 60 minutes, followed by air quenching.
First high temperature is given, after that low temperature is given. Okay.
So, what are the key points to a good age hardening process? The first is to have an alloy that has good properties to this concern. Some alloys simply won't harden, so it is of no use to try this treatment. The second is that the item should have completed all of its deformation and soldering steps before going into the hardening furnace. Annealing again or applying a soldering torch after the hardening would destroy the hardened microstructure. Most easily, you can get information on if one of our alloys is hardenable or not by just checking our technical data sheets, where for each title, the as-cast and after hardening hardnesses are reported. On technical sheets, you will also find the correct hardening furnace temperature. You can also get more detailed information and scientific background on age hardening by checking our JTF archives, where this topic has been extensively discussed. Thank you for watching this video and stay tuned for more technical advices.
See now, what are the advantages of this age hardening? Okay. Say they gives high tensile and yield strength. Then industrial applications also in hardening engineering parts, aircraft parts, etc. And here it does not cause any distortion. Okay, in this age hardening, this is very good advantage. It does not cause any distortion, and also it is one easy machinability also. Okay. Next one, the questions in this topic say, the first one, discuss the strain hardening mechanism in detail. Then what is solid solution strengthening? Discuss in detail the various variables affecting it. Then second question, describe in detail the different strengthening methods for a deformed material. All these are very important. This topic is very important one. Okay. Thank you for watching. Thank you.